Okay, welcome everybody. Good afternoon for those of you for whom it is good afternoon. Otherwise, whatever time of day it might be. Welcome to Hands-On Introduction to Property-Based Testing for Science with your presenter, Zach Hatfield-Dodds. I'm your host. I will be helping out as much as I can during the session. So just to get people familiar with AirMeet, so there's this chat window off to the right of your screen and a Q&A. And then we also have a Slack channel. I can post the name of the Slack channel here in this chat so that you guys can go there. Zach is going to try to keep track of all those three things. I will as well. And then if there seems to be something that gets missed, I'll paste it into the window that is getting more attention, and so that we have a better chance of answering all the questions. So with that, I will bow out and pass it over to Zach.
Thanks, Mike, and good morning, everyone. I look forward to SciPy every year, even when I have to be awake at 5 o'clock in the morning. So let's jump straight into it. The plan for this tutorial is basically to have 4 sections. In each section, I'll give a short talk, then hand over you for some exercises, which we have in a Git repo I'll link to. And then in the middle, we'll have a break. So it's a pretty simple structure. The 4 sections that we're going to go through are like basic property-based testing, just giving you an idea of like, what is this property-based testing thing? You may know already, and that's why you came, or maybe it sounded interesting as a way to raise your testing game, and that's why you're here. Second section is going to be about how you describe your input data with what we call strategies, but more on that later, of course. Then common tactics for tests, kind of like design patterns that are widely applicable or particularly valuable for science. And then finally, the last session is kind of like the miscellaneous stuff that's useful when you actually start applying it in practice. Let's jump into it. Property testing 101. But like before that, what do I even mean by testing anyway? I think of testing as the art and the science of running your code and then checking that you did the right thing. So this is kind of a broad description, but importantly, it actually excludes a lot of things which I think are really valuable for writing correct code, but aren't testing. So like using assertions in the body of your code rather than in a test function. Super useful. You should do it, but it's not part of this talk. Type checkers are great, not always, but often, and not part of this talk. Linters like PyLint or Flake8 find a lot of my bugs, but they're not testing. Code review and coffee and sleep all help us write less buggy code, but they're not testing. A few kinds of things that are testing. We can have unit tests where you write little tests for particular units of code. You can have integration tests for larger units. They're otherwise the same as unit tests. Kind of a weird name, but there we are. Snapshot tests are great where you're not quite sure what the thing should do, but you know it shouldn't have changed. You just like run it and then save the output, and then every subsequent run of your test compares to that known good output. You can have parametrized tests if you have many possible inputs and outputs to check. I am a big fan. We will get to link to the Git repo when it's time for it. No spoilers. Another kind of test is fuzz tests, where we create kind of random inputs and just see if our code crashes. And then, of course, property-based tests and stateful model tests are exactly what we're going to get to later. I should note I'm also going to share the link to these slides with you guys later, so don't need to take notes of anything that's written down here. Let's have a look at some examples for things, and I see the repo links in the chat. This is an example of kind of a traditional unit test style for sorting. And I use sorting because it's like just complex enough to actually show off some of what we're talking about. And here we have 3 unit tests for sorting. We test that if we sort a list which is already sorted, it remains sorted. That if we sort a list which is reversed and maybe of a different type, then we get the sorted list back and it's the correct type, so we're not messing with the numerics. And we can also sort unordered lists of strings, which confirms that our sorting routine doesn't just work for numbers. So far, so good. But if we want to not repeat ourselves, then we might want to use a parametrized test. And so here we're using PyTest. This is actually a little more verbose than the last one, but it's much easier to extend with future cases because we just add the pair of input and known output. So I really like parametrized tests. But what do we do if we don't actually have this known sorted function, right? Like our whole thing relies on knowing the correct result. Well, we can, if we don't want to write the output, compare to a trusted sort function, right? So here we had to write the correct output for each, but if we don't want to do that, or it's not practical to do that, and that's a lot more common in science than in other places, because often the reason we run our code is because we don't know what the result is otherwise. Maybe we have a trusted version of that. In that case, we can just write the input and check that we got the expected output by comparing it to the trusted function. This isn't useful for truly novel stuff, but it's great for refactorings or for performance optimizations. You can do things like, the fast version is the same as the slow version, that kind of thing. You can also write tests even if you don't have a trusted version. And the key here is to stop thinking about testing as finding all possible results or comparing to the correct output, and just checking that you haven't made particular errors. And so in this case, what we're saying is that we don't know anything about what sorted should do, except that the output should be in pairwise order. Hopefully that makes sense. This doesn't find all our bugs, though. We could make it a little stronger by asserting that we have the same number of elements as we started with, and also the same set of elements as we started with. And I actually think this is a pretty good test, but can anyone think of how you might implement sorted to make it pass when it shouldn't? One way to do that would be to have your sorting implementation check if there are duplicate elements in the list and then modify them if so. So for example, if you passed the list 1, 2, 1 and your evil sorting routine returned 1, 2, 2, this test would pass because the output would be in sorted order and you would have the same set of elements before and the same number of elements, but you wouldn't actually have a sorting function, not quite. So we could instead check like the mathematical definition of a sort, that the output is a permutation of the input. This test is comprehensive. It will find pretty much all possible bugs in a sorting routine, but it is hideously slow for non-trivial inputs. So for a fast equivalent test, we'd want to use Python's collections.counter class, which will check that we have the same number of each distinct element in our input, and they're in order. So there we are. That seems like a pretty nice test to me. And the thing I'm going to point out is that these comments are in fact properties, and sorting is fully specified by those two properties, that the output is in order and the same elements are in the input as the output. So we don't actually need a trusted implementation to be really confident that we've got it right. I also want to note that partial specifications are actually still really useful for finding bugs, and they're often a lot easier to find or describe. Don't get me wrong, this test, which just checks the length and the set, is fine. It's not really a plausible set of errors that would make you need this test with the counter class. So where do we go from here? Well, my simple example is that we're still at the point where in this one, we have to manually come up with all of our input examples. And there's a chance that it will behave weirdly for some input that we just didn't think of. If anyone has ideas about that, I'd love to see them in the chat. So this is what it might look like with hypothesis. We use the exact same body of the test, but we use hypothesis to generate our inputs for us. So you say, given an argument, which is one of either lists of some mixture of integers and floats, or lists of strings. And that's because we can compare integers and floats, but we can't compare integers to strings. We just get a type error. Then the same body of the test should hold. Do you think this one would pass? ST is the strategies module. We'll get into that in more detail in a little bit, but that's basically just where all of these special descriptor objects live. This test is actually going to fail because unless we tell it not to, the float strategy will generate nan. And as soon as we generate nan, then this comparison is going to start failing. So what we want to do, in fact, is just say, like, given any list of integers and non-nan floats, then the test will pass. And so it does. So, like, to quickly summarize what I've just gone through, property-based testing is great because often I end up generating input data that I didn't think of, especially when there's many combinations of possibilities, like non-finite floating point numbers, different array dimensionalities, especially like zero-dimensional arrays or arrays of size 0 or pandas data frames with 1 or 0 rows in them. We can check that the result is not wrong, even if we don't know the right answer. And I kind of think of this as like being the scientific method for software, right? That I don't necessarily have to confirm the thing as long as I fail to falsify the idea that my code has a particular class of bugs. And because of this generality, I often end up discovering bugs in my understanding of the problem, where I think that some property always holds and it turns out not to, not just typos in my code. And one thing I didn't show you, but will claim without any evidence at this stage, is that just generating weird input data is surprisingly effective. Like, you get the equivalent of zero division errors or various internal exceptions just by calling your code on really weird inputs. It's kind of like the benefit of publishing it to 1,000 users, except you don't actually need 1,000 users, which is great. Or if you do have thousands of users, you don't have to show them the buggy code to get the feedback on it. So let's jump into a brief session, about 15 minutes, with our testing tutorial. So this is the link, GitHub/rsockle/testing tutorial, and I can see that is also already in our chat channel on AirMeet, and I've just dropped it in the Slack as well. We're going to install the prerequisites for this, which are just Jupyter Notebook, NumPy, PyTest, and Hypothesis. You may have some of these already. And we'll go for 15 minutes of practice there. If you have any questions, feel free to drop them in the chat and I'll respond to those. Otherwise, I will see you at past whatever hour it is for you. For me, 5 a.m. So the file to look at is under Notebooks, and then Exercise 0, the taxonomy of testing. That will look like this. All right. By my clock, that makes it 5:30 in the morning. I hope it's somewhat later where most of you are. If you would like more time on these exercises, feel free to say that in the chat, but otherwise I'm going to default to moving through. The first set of exercises is designed sort of as much to get you familiar with the tools and the repo that we're using as it is to actually do exercises. Because you might have noticed they're mostly pretty introductory. They use hypothesis, but really just to make sure that you've got things installed. And in particular, going through them is going to make hopefully a bit more sense once we cover how to describe your data. And that is section 2 of the tutorial. We'll have some more time for these next exercises as well. So in this section, we're really going to be focusing on what we call hypothesis strategies, the way that we describe the data that we want our test to generate. And I'm going to give you a pretty intensive walkthrough of the various strategies that we have, and then some useful recipes for how to use them. Important to note that in this section, we're really focusing on how to generate data, not what to do with it. That'll be the next section. But to be honest, just generating exhaustive or weird data is already a pretty useful way to start. So we've got scalar values, collections of values, modifying them with map and filter, a couple of special strategies that are really useful for composing things, 3 different ways to create recursive data, depending on what you want, and then how we infer strategies in various ways. And finally, like a quick breakdown by where you would import them from. So scalar values. If you've been working with NumPy or pandas, the idea of a scalar should be pretty clear. It's like a single number or a single string or something. So we have none and booleans, numbers, integers, floats, fractions, decimals, complex numbers, strings, whether you want single Unicode characters or Unicode text or byte strings. And for numbers, we have numeric minimum and maximum value bounds. For strings, we tend to have minimum and maximum size, so you can determine the length. Gerard, the difference between a runtime error and a PyTest error will generally be in the test status. If you have an error because you've run the test function and it failed, it should say failure. If it's because PyTest couldn't run the test function for some reason, you should get an error instead of a failure. And then other scalar values that we have will be things like dates, times, time zones, and a whole bunch of other things that I've omitted for space. But our documentation will list them all and links to that a little further on. For collections, there's basically 3 categories. We have the list strategy and things that are kind of like lists. So this takes an elements strategy. So that might be integers, or it might be booleans, or it might be date times that we saw earlier. We have a minimum and a maximum size. If you don't specify those, then 0 or more elements. And then we also have optionally whether or not it's unique in some way. And unique by can be like a function or even a tuple of functions if you wanted to do that. And so this strategy is broadly useful if you want to create a collection of some variable size with elements that are substitutable in some way. And under the hood, this is actually how we implement things like the dictionary strategy, sets, iterables, and much more. The tuples strategy is a little different. It's fixed length. You pass it however many strategies you want, and it creates a tuple of that many elements, each element drawn from the corresponding strategy. So if you want, for example, an integer, and a string, you would call tuples, integers, integers, text. And then fixed dictionaries, you pass in a dictionary with the key and then a strategy for the value corresponding to that key. And you can have those for both required keys and also optional keys. If a strategy doesn't generate exactly what you want, the map or filter methods on every strategy can be quite useful. So the map method, kind of like a pandas map, will generate an example from the inner strategy and then apply the function. So if you take integers and then map string, you'll generate a random integer and then call string on it before handing back the result. And so you get strings of digits, possibly with a minus sign in front of them. The filter method is a little different. It's great for rejecting some inputs, but best used when those inputs are not super common. So for example, if you wanted to exclude 0, filter would be a great way to do that from all your numbers. If you wanted to exclude negative numbers, you would be better off passing the minimum value argument. There's also hypothesis.assume, which is like a function you can call anywhere, including inside functions that you're calling with map, or like inside your test function as well. And that's equivalent to the filter. Basically, if that gets called with a falsy value, or like your function returns false inside the filter, hypothesis will throw away that test input and try again. And that means that just for efficiency reasons, if more than something like 20% of your examples are filtered out, then you should probably try to find a different way of doing that. And so, for example, if we want a ordered pair of 2 integers, you could call this with a filter. So you create your tuples of integers strategy. You could filter this and just say, if it is ever the case that the first element is not less than or equal to the second element, discard that and try again. But naively, we would expect this to reject almost exactly 50% of the inputs. So we're actually better off calling map to sort our elements for us. And in this case, we can just chain calls to map so that we sort it, and then we turn it from a list back into a tuple. So the just and sampled from strategies are our 2 first special strategies. Just is kind of useful because it gives you a strategy where you actually just want only ever a single value. And the classic example for me is like where the time zone should only ever be UTC. But if you want to pass the other arguments using hypothesis, this makes it easy. Or if you want to compose that with a broader strategy, just lets you kind of lift values into strategies, but it will only ever generate the exact value you pass to it. It's worth noting that that means that, like a default argument, if the value is mutable, you're going to run into some really weird effects. And then the sampled from strategy is kind of that, but where you've got more than one possibility. So for example, maybe you want like an inner join or an outer join, and you want it to be possible to have either of them, then you can sample from that. And if you do it with a nums, then it can also generate combinations of nums if it's marked as a flag. The one-of strategy kind of takes the union. So if you have one of integers and text, then it can generate either integers or Unicode strings. And nothing is basically the empty strategy. It will never generate anything. And so it just gets discarded. If you have like one of integers or nothing, that's just the same as saying the integers strategy because the other branch can never be taken. The main reason we have this is that it's much nicer to kind of have this as the empty strategy because it means that you can just be confident that you always have a strategy instead of needing a different sentinel value like none. I should note, though, that while we can combine strategies with one of, there's not in general any way to say, like, only give me examples that either of these strategies could have generated. The build strategy is another one that we're going to use all the time. It's great to construct custom objects. Like if you have your own classes, builds is pretty much where to start. It starts off looking kind of like this complicated invocation here, where we draw, you have your thing to build, and then you have arguments and keyword arguments, which are the strategies to pass to it. We draw a value from each of those and then pass them to the thing to build correspondingly. The actual build strategy, though, has a bunch of error handling and syntactic sugar, so it's a little nicer to work with and gives you much better error messages. It also has a nice thing where if you have required arguments, it will actually infer the strategy for them based on any type annotations. More on that later. And then finally, if we have recursive data, there's a couple of different ways to do that. If you're using composite strategies, you can just write recursive function calls. Or in general, like you can often just write recursive function calls and that will just work. There's a strategy literally called recursive for if you have something that looks a lot like JSON. And so this example will actually generate any possible JSON object. We say, well, JSON is none or true or false or a number or a string. And then the JSON collections, this is the base case, are like lists of any JSON object or dictionaries of strings to any JSON object. The deferred strategy is another great one. It lets you define forward references if you have like mutually recursive things. If you have a name error, it's a safe bet that you can just wrap your thing in deferred and it will probably work. And my favorite time saver is inferring things with from type. This is basically designed to let you avoid repeating yourself. If you've already type annotated something and you do mean that any instance of that type should be possible, Hypothesis is almost always able to just guess how to generate that and do it for you. So it is designed as a time saver, and if it's not working, then you might have to write the thing by hand. But we've also been really careful to make sure that from type combines well with all the explicit strategies. You shouldn't have a thing where either it's fully inferred or fully specified. You should be able to specify only the parts you care about and let Hypothesis guess the rest. And for your custom types, if you have particular requirements, you can register a strategy to use for that type wherever else it comes up in your code base. There's a couple of other inferred strategies. One that you'll probably use a lot in data science is from Regex. If you have a regular expression that you use to validate, Hypothesis can run that backwards and actually generate strings that match a regular expression. And for the NumPy fans among us, there's from dtype to generate scalar or struct values, which can be represented in a particular data type. And if you really, really like linear algebra or more complex functions, there's the mutually broadcastable shapes function. And that will give you array shapes that can be broadcast together, possibly with respect to some function signature, such as matrix multiplication. If you're writing your own inferred strategies, just a couple of tips. First of all, it is actually a really useful pattern to write a function which takes some kind of object or schema or spec from your code base and returns a strategy for conforming things. But just some advice, it's much better to err on the side of generating too many things rather than too few, because having your test silently pass because you were conservative rather than failing because you needed to specify something by hand is a lot worse. So explicit is definitely better than implicit. And I mentioned before supporting that path from fully inferring the test to fully specifying the test. You don't want to make that an all or nothing proposition because it makes it a lot more awkward. And to be honest, it also drives people to do unwise or esoteric things with code generation if they would have to do that instead of just specifying a little bit of the test for themselves. So another set of like special or combination strategies. We have composite and flat map and data. And these are all ways to generate things that have internal dependencies on other parts of the structure. So for example, a list plus a valid index into the list, or a data frame plus a chosen row from the data frame, or a column and then a subset of the elements in it. In simple cases, you can also just work with FlatMap. And what FlatMap does is it takes a strategy, generates an example, and then passes that to a new function, which returns a strategy, and then FlatMap draws the example from that strategy. So this cute little invocation says, we take the type, we generate any instance of that type, which is what the from type thing does. And so this will be a type object. And then we apply from type to the type object that we got and generate any example of that. So from type, flat map, from type will generate an instance of any type that Hypothesis knows how to generate instances for, which I think is a pretty good trick. On the other hand, if you're doing anything that's like more than one line, just use the Composite Decorator. It basically lets you define a function where the first argument will be passed in for you as a function which takes a strategy and returns a value from that strategy for you. So, for example, you can get a factory, then get some kind of power setting, which is between 0 and the max voltage of the factory that was created, and then returns a widget that could have been made in that factory. Composite things tend to be particularly useful if you have like a common data type or a common semantic thing, like maybe you want data frames with particular properties or columns. This is basically how you define your own functions that return strategies. Super useful. I'm also going to show you this, which I call the inner composite trick. It's especially great for reusable strategies because it lets you separate out the validation of the arguments the user passes from the code that actually does the thing at runtime. And that means that you only ever pay the performance cost of validating your inputs once while still having input validation, which is quite important. But in this case, we don't actually need composite at all. We could just build a widget made from some predefined set of locations. So often, the inner composite trick is cool, but just do make sure to check whether you need composite at all. A function which returns a strategy is totally a thing and often simpler. The data strategy is basically like composite, but it gives you the draw function inside your test. So this is like the most powerful possible thing to do with hypothesis. It's incredibly flexible, and it lets you decide what data you need based on the behavior of your test so far. The downside is that, well, it's super flexible and powerful, maybe more than you need, and that means that the error reporting gets a little more complicated. So use data if you need it, but if composite would work, do consider just using the simple tool first. And then the final part of this short talk before we go back to another set of exercises is where to look if you're looking for particular strategies. So for core strategies, which is just the standard library stuff plus a couple of backports for old versions, is found in the hypothesis.strategies module. And in our docs, that's at hypothesis read the docs.html, and I'll drop that in the chat as well. For extra strategies, this covers stuff like NumPy and pandas, and also like date times and Django and so on if you do that. That's found in hypothesis.extra.numpy.pandas.django and so on. I expect that we will probably be using more of those in this tutorial than in my general audience version. And for third-party extensions, you can actually find many other libraries which provide hypothesis strategies customized for them. Sometimes that's strategies, sometimes that's functions to infer a strategy, sometimes that's explicit plugins. For example, Pydantic, like FastAPI, actually has a built-in hypothesis integration. And do note that just because we know about them and list them in the docs doesn't mean we endorse them. Standard disclaimer. So what I hope I've covered here is that strategies are kind of primitive things that you can combine to generate your data. We provide a lot of those primitives, but how you combine them is essentially up to you. And I kind of think of this as a duct tape mindset. Like if it's not working, just use more of them. All right. Happy to take any questions from the Q&A now, so I'll tab over, and then we'll jump into exercises for the next part. You're welcome to do the exercises in Jupyter Notebooks or in your IDE, whatever works for you. Otherwise, let's give ourselves 20 minutes this time. So we'll come back together at, say, 25 minutes, quarter past the hour, and then after that, we're going to take our short break. So feel free to jump in with questions in the Slack or on AirMeet, and I'll be happy to answer them as we go. All right, everyone. So we're coming up on 25 minutes of these exercises. I'd love to see in the chat just where people are up to. Do we want to take some more time on them, or are people finished and ready to move on? All right. So it sounds like people are doing pretty well, but would like some more time. So let's give this one another 10 minutes until half past the hour. I've also just dropped the instructor solutions link in the chat. So if you want to see the complete solutions, you can go to the instructor branch and then back to notebooks. The file has a slightly different name, so just changing branch unfortunately doesn't bring it up. So the problem we run into in this example is just that NumPy data types are not actually objects of type. So if we have it here, we're going to want and that also doesn't work. But you can see the first example it tries is 0 in the base strategy, and then gets 1 added to it. Where this gets really fun is if you're dealing with non-scalar data types, such as, for example, a pair of an integer and a float. So usually that would be like an XYZ coordinate. Carl, I'm not sure exactly what you want to build here. If you were building, say, Apple. All right, everyone. Coming back together, that marks our break time. That's a bit of an anticlimax. But if you're going to stand up, stretch your legs, get a coffee, this is a great time to do it. And we'll be back in 10 minutes. So at 10 minutes to the hour, back here, please do take some time off exercises for a stretch. I'm going to stand up now. Keep dropping questions in the chat. Happy to answer those or give you demos in the Jupyter Notebook. See you in 10 minutes. All right, welcome back, everyone. I'm going to call that the end of our break and get ready to move on with part 3 of today's tutorial. Down in Australia where I am, the sky is lightening up. So we've got the beautiful pre-dawn dark purple shading into dark blue now. So I'll be sure to let you know when the sun rises. But for now, on with the show. So just a refresher. The plan for today was that we were going to do a tutorial in 4 parts, and we're past the first 2 parts now. So we've done our basic property-based testing, and we've learned a bit about how to describe data using hypothesis. Now we get on to the fun parts where you really learn how to find bugs. We're going to start with some common test tactics that you can apply, and then our last session of the day will go into more detail about configuration and other practical topics. So, test tactics. I called them strategies, but the word is taken. Strategies would also be called generators, except that word is also taken. You know, as they say, naming things is hard. So we're going to split this into 3 parts. The first is common properties that can be applied to almost all code bases. So those are the simple fuzzing, or like it doesn't crash when I call it property, which should be true of everything. Round trip functions, equivalent functions, and then metamorphic properties, which are complex but awesome. Then we'll talk briefly through some more situational properties, which are good in specific contexts, but may or may not fit yours. And then finally, I'm going to give you a demo of ghostwriting tests, which is really cool. First property. Your test function just calls the code. Nothing else, it just calls it. This is embarrassingly effective on my code. It turns out that when I write a function, I usually forget to handle some weird interaction of edge cases. And a science example, it turns out that if you have a 0-dimensional NumPy array which contains nan, everything breaks. Like really weird stuff happens. Or if you have dimensions of size 0, or if you have overlapping or like non-scalar data types. And this is a common kind of thing where the code will work for like the happy standard path, and it will also work for any one weird thing of all the various like feature dimensions that you have. But if you have some input which exhibits multiple weird behaviors, often just calling your code with a weird input like that can turn up all kinds of bugs. The second one, which is a little more complex, is round trips. And so this is the idea that, for example, if you save your data, then load your data, you should get the same data back. Or if you encode it, then decode it, or send it and receive it, go between data formats. These are pretty much always critical functions in our code base. They have relatively complex inputs and outputs, especially for saving or serialization function. And the errors are quite common because they tend to be silent logic failures that corrupt things. But they also cross many layers of the programming stack, especially like saving or loading or serializing data. Okay, I just got a connection might be lost notification.
Yeah, so the video disappeared, so you'll have to reconnect the video.
Okay, let's see, I can do that. It wouldn't really be an online conference without the tech going wrong at least once, would it?
You're back up.
Excellent. Thanks, everyone. So the last thing I have to say about round trips is just like, seriously, test your round trips. This is the single most valuable kind of test that I write. In fact, writing tests like this is literally how I started using hypothesis. I had this nasty scientific problem with like a point cloud of 3-dimensional points. And because the input file was like 14 gigabytes, it took about 12 hours to run my code. And then right at the end, when I went to save my computed output, the code would crash. And if your edit, run, debug cycle is 12 hours long, you have a lot of time to discover other tools like hypothesis. So good work, everyone, for choosing a faster way like this tutorial. The third kind of common property is equivalent functions. And this actually comes up quite frequently as well. For example, you might have the old version versus the new version, or like the single-threaded versus the multi-threaded version, or with NumPy, like passing optimize equals true or optimize equals false to einsum that actually did find a bug a while ago. You might have that applying functions in a different order should be equivalent. And then sometimes you have functions which are equivalent for some particular subset of the inputs, or where one of the functions only handles a subset of inputs, but where it handles that, they're equivalent. We saw this right back at the start comparing to a trusted sorting function. The thing here is it doesn't have to be a totally independent implementation. Even just varying parameters that shouldn't matter can be a great way to check that they actually don't matter. And then validate the output. I always feel really silly when I write these tests, but then they find bugs and I feel like I'd be even stupider if I hadn't wrote them. So numbers are in the valid range. A classic one would be my probabilities are between 0 and 1. Or you got the expected type, or that your string is not empty or doesn't contain a null character. The important thing to note is that often these kind of output validations can actually be located in your code rather than in your tests. The idea of putting assertions in your code can be a little controversial at times. Many people say don't do it, it's not a best practice. That's usually because they're thinking about things like authentication checks in a web app, where you assert that the person is logged in. And for those cases, it's true that it's not a good practice, because if you run with the Python optimized environment variable, your assertions don't get checked. And that means you should never use them for anything security critical. But if you're thinking of a logical correctness check, that actually makes assertions perfect, because if you really need to turn them off for speed, you can do so with an environment variable. And the rest of the time, you can get this joint benefit of getting local fast feedback in your tests. So your code fails as soon as your expectation is violated, rather than when you have the assertion in the test function. And also you get to test in production. I would almost always rather crash than silently handle or write out invalid data somehow. We're into more specific properties here, but these are the ones that property-based testing is actually named for. Yeah, that's a great point, Michael. Exceptions for things that shouldn't happen and assertions for things that you're pretty sure can't happen. So if an assertion ever triggers, that should be because there's a bug in your code, not because something unexpected happened. So these properties like idempotency, commutativity, associativity are the algebraic properties, which is why Haskell developers named this style of testing property-based testing. They're not that common in Python code because we don't tend to adopt the pure functional style. But if you have them, it is totally worth testing them. And for example, sorting is idempotent, addition is commutative and associative, at least on the real numbers. And if you're implementing something like that, it is absolutely worth checking this kind of thing. For the slides later, this is a great blog post where these kinds of algebraic properties actually did come up in a data pipelines problem, where you had certain nice kind of properties about how function or pipeline composition should work. We'll see more of these later. The last one that I was going to talk through was what we call model-based or stateful testing. And so honestly, to go into this in detail would be a whole separate workshop. So I'm basically just going to describe it to you, and then you can look in the docs later. The idea is that the ones I've shown you so far, you get a hypothesis to generate some data or some inputs to your test function, and then you take actions. With hypothesis stateful testing, you define a class with various methods, and then a hypothesis doesn't just choose the inputs to each method, but it also chooses the order to call them in. So this is really great for exploring some kind of stateful API, where you might create an object, then mutate it, then query it in some way. But I'll leave that to the documentation. Metamorphic relations are super powerful, and they're really useful where you don't know what your code is meant to do yet. A metamorphic relation is a relationship between two separate inputs to the program. So the classic example that I've kind of stolen the diagrams for here is that if you generate a random program and compile it, then execute it on some input, then mutate or delete any code that wasn't executed by that input and compile it again, and run that same input on the new program, you should have the same output. But due to compiler optimizations, this paper found, it turns out that this is often not the case. More simply, you might have something like your code should be scale invariant. So if you double all the inputs or multiply by whatever constant factor, your output should be equivalent multiplied by that constant factor. And this means that you don't actually need to know what the output should be. You just need to know that your code should be scale invariant. You might have like equivalence of function composition, like this is pretty much what we saw before. Or we might have relatively simple properties, like if you're writing a tax code, you might say that it should always be the case that if your income increases, your post-tax income also increases, right? We never want to have a situation where someone's marginal tax rate is greater than 1. So by earning more money, they keep less of it. That would be a terrible incentive to set up. Another good pattern is like if you add an operation that shouldn't make any change, then it doesn't make any change. Metamorphic relations are definitely something that takes some practice to identify, but they're among the most powerful like meta patterns for tests that I know of, and they're especially valuable for scientific code. But the big takeaway from this part that you should leave with is like write assertions, fuzz your code, check your round trips, and then relax. Like if you do that, you'll have gotten a large chunk of the benefit out of hypothesis with a tiny fraction of the work. All right. Are there any questions about the properties I've talked through before we go on to the live demo part of the talk? All right, I'm going to take that as no questions at this time and on with the live demo. Let's say that you're only halfway through the tutorial, but you're just sick of writing hypothesis tests already. This is a kind of sad situation to be in, but hypothesis is here to help. Hypothesis can actually write your tests for you. The hypothesis write command can be passed a module or a function name, and optionally like one of these patterns that we've seen, and maybe even like allowed exceptions. So let's just try writing a hypothesis test for a sort function. If we try doing this, we will quickly see that there is in fact no sort function. Let me zoom in a little further, sure. Hopefully that works. Awesome. So if we write for the sorted built-in, we get a property-based test. Hypothesis will do a bunch of introspection and notice that there's an argument called iterable, and it will guess that that should be like an iterable of integers or an iterable of text. There's an optional key function. And the key function here is optional, so it can be done. In reality, it could also be a function of some kind, but hypothesis doesn't know how to write that, so it just leaves it as none. And the reverse might be either true or false. So we can run this test and it will pass because the sorted built-in has been pretty well tested already. But we could also tell hypothesis that the sorted function should be idempotent. That is, if you call sorted on the result of sorted, then it shouldn't change. And sure enough, we calculate our result, then we repeat that by calling it on the result, and we assert that they're equal. So this seems pretty convenient, right? Let's try writing an assertion that two things are equivalent. And the ones I'm going to use here are the literal eval function and the eval built-in. Literal eval is great because it's a lot safer than evaluating arbitrary code, but it also only works for a subset. And here we're going to see that we have to actually write some more detail about what we want. So hypothesis can produce a template for us, but it's not actually quite complete. Because here, for example, we've got node or string and source. Those are the respective source code inputs. So we're going to want to replace one of those with like a strategy for Python source code and just delete the other and make sure we fix up the test a bit. The ghostwriter is neat, but it's not actually magic. If we want to write one for those classic algebraic properties, for example, for the properties of addition as a binary operator, hypothesis can tell that maybe it should be associative, maybe it should be commutative, and maybe there should be some kind of identity element. In this case, what we're going to want to add is change this operand strategy to numbers, for example, so maybe integers and finite floats, and then specify our identity element. And for addition, that's 0. 0 plus anything is equal to whatever that thing was. All right, another test. Let's look at a round trip. Compression is kind of a classic one because if you compress something and decompress it, you should get the thing back. And hypothesis is smart enough that if you tell it about a compress function, it will notice that there is a decompress function in the same module and guess that that should reverse the original function. Does this make sense so far? Excellent. Let's look at a kind of scary one, the JSON dumps function. So this takes a JSON object, like some mixture of like lists and dictionaries and strings and booleans and numbers and none, and encodes it to a string and then brings it back to that original object. And oh my goodness, there's a lot of arguments here. When I ran this for the first time, I'm like, parse constant, there's a separate parse constant argument. Okay, so there's a lot of stuff here. But the only thing we really need to care about is nothing. This obj strategy is the bit that we need to modify. And so just to make things simple, I modified the test that this output just by deleting all the stuff that I didn't actually care about. And so this slightly shorter version, we allow whether nan is allowed or not to vary. We say, well, check circular. We're not actually going to generate any like self-referencing objects, but if the check is enabled or disabled, shouldn't matter at all. So we'll still allow it to vary. Whether or not we ensure that the output is ASCII or allow like full UTF-8 can also vary. Indents, we haven't specified here. Like you can modify this so it's like none or a number of spaces or whatever white space you want. But the important bit is here where you remember I showed you that little JSON example before. We've got our recursive base case and our extension for JSON. We won't specify the separators and like whether or not we sort keys in dictionaries or objects in JSON, we'll allow to vary as well. And if we dump that and load it, we should get the same thing back. What do you reckon? Will this pass? So, hypothesis finds two distinct failures for this test. And this is kind of a neat trick that hypothesis can actually report multiple distinct errors if it finds them. And so we've gone, if allow nan is true, check circular is false, ensure ASCII is false, indent is none, and our object is nan. Here's the key. Of course, nan is not equal to itself. So our test fails. But that's not the only thing we found. We also found that if allow nan is false and our object is infinity, then we actually get a separate value error. And that's because infinity and nan are not strictly compliant with the JSON spec. Python allows them to be encoded by default, but if you pass the strict argument, that's the allow nan equals false, also disables infinity, it turns out, then we're going to have a problem. So let's have a look at the diff for where I've fixed up this test a little. We're going to say that nan and infinity is always allowed here, and we'll use the assume function. This is kind of like a filter, which says that like if the object is not equal to itself, just reject that input. Can I get like a thumbs up or thumbs down react for if you think this test will pass or fail? All right, let's find out. We've done better this time, but the test still fails. It turns out that a list containing nan compares equal to itself until we round trip it through JSON. And the reason for that is that there's a couple of performance optimizations in the implementation of list equality. It goes like, if self is other, return true. No thumbs down, that'd do it. So if the other list is the list you're comparing, then like they're equal by identity, and by Python's object model, that should mean that they compare equal as well. nan just kind of breaks that. So let's try the proper fix, which is just to say that like nan is not allowed. We're still going to say allow nan equals true though, because that lets us generate infinity. If you want to handle like all of these interacting edge cases, I would probably just end up writing 2 tests. And do we think this test will pass? It sure does. So it turns out that I originally wrote a test like this literally for a demonstration on some slides at a conference talk, and I was so confused when it failed. Like I learned a lot about how Python lists work by writing this trivial demo test. And I think that's pretty cool. All right, I don't have NumPy in that virtual environment, but if you've got Hypothesis installed locally, Hypothesis write NumPy will write you a lot of tests, and it's kind of worth checking those out. The ghostwriter really does as much as I could work out to try to create these tests for you. It will look up all the functions. It will look at the argument names, at the argument types. It will also read docstrings if you're using like Sphinx or NumPy docstrings, which list the types. It will use that. But the thing to remember is like the ghostwriter is not magic. It gives you a starting point, and I hope you'll find it useful. Third set of exercises goes through, and we're going to look at writing tactics for various things. So let's allow half an hour for this one. I will see you back here at 1:45. So for me, 7:45 a.m., when hopefully the sun will have risen. See you around, everyone, and feel free to post questions in the chat.
Zach, you're not presenting anymore if you wanted to be.
I just shut that off while I was working on some other stuff.
Okay.
It was just the exercises slide. All right. Welcome back, everyone. How have people gone with those exercises? Thumbs up icons or drop in the chat. Are we ready to move on to the last section of the tutorial? All right, then. Let's get to it. Section 4 of the tutorial is putting it into practice. And this is where I cover like all of the random miscellanea, like configuration, integrations, and support channels that might be useful if you actually want to use this in the real world. So we'll talk through some design patterns for your test suite, not just like the patterns for the test itself, but how to use them as part of a broader testing strategy, including importantly when not to use them. We'll talk about settings and settings profiles. We'll talk about the example database and how to use it. And then a little bit about coverage guided fuzzing and the broader kind of context here. One moment. All right. And then our final exercises, if we run through that early, will be to actually hunt for some real world bugs, apply it on your project, and then ask me any questions you have about getting that set up. So the first thing I want to emphasize here is I've talked a lot about how cool property-based testing is, how much I like it, how much you can do with it. It is not a panacea. And I would definitely not use only property-based tests. But just as I think that 100% is the wrong ratio, I also think 0% is the wrong ratio. Depending on the project, I tend to write something like 10 to 90% of my tests as property-based. For hypothesis itself, that's probably about 30 to 50%. For hypothesis JSON schema, an extension I work on, it'd probably be more like 95%. When I wrote tests for the black auto formatter, they just have one test, which is that it runs on any valid Python source code without crashing. And that's found like 5 different bugs for them so far. So do use property-based testing, but don't abandon your other forms of testing either. There's a great pattern actually where you can find existing tests that you have, whether they're parameterized or existing unit tests, and just think about like, what details have I written into this test that I could instead allow to vary? And that can kind of help you migrate a bit and keep the value of your existing tests, especially if you use the @example decorator to preserve those current inputs. The second pattern here is writing custom strategies for your project is a great way of kind of sharing knowledge or having a single source of truth about all your weird edge cases. And that means that when you need to update that, like if you add a new feature or you support a new data type or something, you can update that in one place instead of having to edit every test simultaneously. And then like I've shown some of these earlier. Functions which return strategies are really useful if you have like a general pattern for your data that you occasionally want to vary, or just like assign some global values that you import or put them at the top of a test module. And for custom types, there's register type strategy. If you're working on an open source library, we also have a plugin infrastructure, which I won't cover, but you should look into that to automatically set this up for all of your users. Can I get like a wave from people who use print debugging all the time? Hi, everyone. I use print debugging all the time. If you do that with hypothesis, though, you'll get like 100 print outputs, and that's a pain. So we supply the note function. It's like print, but it only actually prints during the last example. Print debugging. It can be great. If, on the other hand, you want to see some kind of summary over all of the examples that hypothesis tries, the event function is pretty similar to print, but we then summarize like, okay, 40% of your examples did this, 20% did that, and so on. If we look at those statistics that I mentioned, this is kind of what they look like. You run with like -- hypothesis shows statistics, and you'll get your runtimes, you'll get some information about how many passing and failing and invalid examples, like ones where too much was filtered out, it couldn't prepare that, as well as the events, which is here. And then during the shrink phase, it'll tell you what else it tried and why it stopped. In this case, nothing left to do. It had shrunk to a minimal example, so we're done. Usually that should be stopped because we tried like 100 examples and that's how many you told us to try. Randomness is another thing that people ask a lot about. If hypothesis is random testing, doesn't that mean it's flaky? Broadly, no. Hypothesis should never be flaky. We have a lot of internal stuff and we've spent years working on this. But if you're dealing with like an external random number generator, there's a couple of options. Because this does come up in things like simulations, for example. The best option is if you can pass an instance of the random class, we have this st.random strategy to generate those for you. And that'll have like a known seed and so on. On the other hand, if your randomness is more like thread timings, that's basically just out of scope. Like if your code does different things depending on the order that the kernel schedules threads, maybe just run it single-threaded for hypothesis, I guess. If you have like a global random number generator though, you can look at the random module strategy, which will set the seed of all the global random number generators we know about. And like NumPy is handled by default, so you don't need to worry about that. And if you have something else, you can call register random to add it to the list of things that we handle for you. Again, like if you're an open source library, feel free to ping me and I'm happy to write you a plugin so that when your library is imported, it will automatically register your global randomness. Settings. I mentioned earlier when we were looking at this that how long we run for is actually determined by hypothesis settings, and here they are. You can set settings as a decorator on your function, or use profiles, so you have some kind of global defaults. And the reason we have profiles is so that you can easily have different settings, for example, a different deadline or different number of examples in local development, in CI, in like pull request CI compared to a weekly long test run. And you can select those either from code, so you can set them up however you usually deal with config, or as PyTest command line options. And a couple of the important options that we'll cover. There's the deadline per test case. By default, hypothesis will warn you and trigger a health check error if any individual input takes more than 200 milliseconds to run. For some things, particularly if you're working with pandas data frames, this will often be too low and you should set it higher. But the idea is this kind of warns you if your test is not fast, on the basis that we would rather be explicit about that than have sort of silent performance regressions. The other one that you'll probably change all the time is max examples. This one is pretty simple. That's the number of inputs that hypothesis will try to generate for you. It's pretty obvious, I hope, that even though hypothesis adds relatively little overhead, running your test 100 times will take about 100 times longer than running it once. So if that's too much, you can turn this down, though I wouldn't turn it down below about 20 in any case. Or if you want to be really confident, you can turn it up to like 1,000 or 10,000 for occasional test runs. There's also, if you really want deterministic runs, where hypothesis will always run the same examples, you can run with the de-randomize equals true setting, or hypothesis seed from the PyTest command line. This is particularly useful if you follow this kind of pattern that Nelson Elhage writes about, where your CI tests are designed to only check for regressions. So you actually don't want to discover new bugs there, and then you have separate test runs where you're searching for new bugs. So that's a great case for like writing your explicit examples, running de-randomized with a small example cap in CI, just to find regressions. And then in randomized mode with a really large example cap in like nightly CI runs to find new bugs. I wouldn't tend to worry about that unless you have a relatively large team working on the same project together. If you want to reproduce a failure, the first thing I'm going to say is like, just rerun the test and hypothesis will actually have remembered what the failing example was. If you want to be really sure that it's always reproduced on someone else's computer, for example, you can use the example decorator. And that was in one of the earlier exercises if you got to it. So hypothesis will always start by executing each explicit example before going on to generate new examples. If all else fails though, and if you're reproducing stuff from a CI system, sometimes this is useful. The print blob setting will actually just dump like the base 64 encoded sequence of choices that hypothesis used. And this is basically guaranteed to reproduce it. Hypothesis will do exactly the same thing because this is like the random seed, but also. Since I mentioned sharing the database or like not having it shared between computers, I should talk a little bit about this. By default, Hypothesis database is literally just a directory full of files which contain like the random bits that generated a particular input. You can share that. You can even commit it to Git. We don't tend to recommend this because it's an opaque binary blob and it's not guaranteed to be stable between Hypothesis versions. And so our recommended option is actually just to implement your own example database class. We ship one that operates on top of Redis. You just point it at your network key value store, and then that's where Hypothesis will store all of the byte strings for you. We're also showing off like a neat little profiles trick here. So we say like in CI, always use the shared database that's stored on the network and common between like all our CI runners. In local development though, multiplex over our local database and a read-only access to the shared database. If you set up this pattern, then reproducing any failure that occurs in CI is literally as simple as just rerunning your test locally, and Hypothesis will pull that same example and rerun it. I found this to be a pretty neat trick, to be honest. Another cool trick or feature is guided testing. By default, Hypothesis is pretty much a black box, so it uses a bunch of heuristics and some tricks to get a kind of diverse sample. So it's better than uniformly random, but directed search is kind of qualitatively better again. So the way this works is that you call Hypothesis target with a real number like an integer or a float score to maximize. And if you've got multiple scores, you can pass a label, for example, for your X dimension and Y dimension. And then Hypothesis will systematically try things that are related to the current best known example. Or if you've got multiple, to like everything on the Pareto front for multi-objective optimization. A couple of uses that we found for this, which are surprisingly powerful. If you have like an error bound on some computation, you've got a certain maximum error, then you can just target that the absolute error is less than your threshold. And this will both assert that, if you assert that my target is less than my threshold, but also it will inform a Hypothesis about like how well it's doing, like how close it is to falsifying that. You can try to maximize like the number of steps taken, the number of tasks in a queue. You can try to maximize runtime. That one's a little tricky because runtime is often a little bit non-deterministic. So if you can get like the count of steps taken, that's usually better than a wall clock measure. You can also target things like compression ratios, or if you want to avoid filtering problems, like you're saying, we want to try more examples which are valid than invalid, but either should be possible. You can just like target based on whether or not it was valid, and Hypothesis will spend most of its time trying variations on valid things for you. My personal favorite usage of this was in AstroPy, where we discovered that the time conversion regime routines were something like 20 billion times less accurate than we thought. 20 billion times is like a big epsilon for your error. We can generalize this idea of guided testing with what's called coverage-guided fuzzing. And the best implementation of that for Python in the traditional vein is probably Google's new Atheros project. It's a wrapper around libfuzzer, which is the classic C tool, designed to run a single function for like hours or even many days. Hypothesis test by default, each execution takes maybe a few dozen milliseconds. You have 100 of those. So you're mostly looking at like sub-second per test for the unit tests. If you run it for hours though, you can use coverage instrumentation to learn what kinds of inputs produce what kind of behavior and to sort of evolve your way through the program state space with a genetic algorithm. Because Atheros is designed for C, it works beautifully for C extensions and for native code because it can do the coverage of both the Python and the C code simultaneously. And Hypothesis integrates really well with this. You can actually use a traditional fuzzer which produces byte strings to drive Hypothesis. Every Hypothesis test has this attribute hypothesis.fuzz1 input. If you pass that a byte string, it will execute the test as if we had randomly generated that byte string as the underlying seed. I didn't particularly like the user experience of this, though. So I've actually started a little company selling the hypothesis extension for test suites, which is HypoFuzz. And the idea here is that it runs all of your tests at once. So it will dynamically prioritize whichever one seems most useful. So if you have a single test that you really want to hammer on, definitely use Atheros. If you have a test suite that you want to hammer, check out HypoFuzz. I think that maybe I'm biased, that this has much better integration with people's workflows, especially for teams, and it has fantastic support for the hypothesis database. Though, again, not better than anything else because the database is just awesome wherever. You can use the same tricks regardless. If you need support for hypothesis, per the support page, we do not offer free support, but Stack Overflow and the mailing list are usually pretty helpful. And if your company has a budget for support or training, we do training, whether it's running a workshop like this or doing intensive pairing to get you set up. So if you start using Hypothesis, you might notice that our release frequency is high. And that's because we have continuous deployment set up so that every pull request actually gets cut as a new release. Therefore, update on a schedule that works for you. For some people, that's just updating every time. Most of our users probably, if you pin your versions, which I strongly recommend, update on whatever schedule works for you. So for Hypothesis itself, we have a weekly bot that will update all our dependencies. We do take stability extremely seriously, so I do not know of the last time we had a compatibility break or a regression aside from our scheduled major releases. But even those almost never break compatibility. And in fact, last time when we moved to keyword-only arguments for some functions, I actually wrote a code mod which could automatically refactor code in order to add the keywords in the calls which you now need keyword arguments for. All right, that's the practical stuff. So we've got a little less than an hour left of this tutorial. I'm going to suggest we take maybe half an hour for our last set of exercises and then come back for some Q&A right at the end. Does that sound good? Awesome. All right, all the best, people, and I'll see you in half an hour. Hey everyone, with about 20 minutes to go of our tutorial, I thought I'd bring us back for some final demos and Q&A before we wrap up. So any questions, dump them in the chat and I'll be happy to have a look. Otherwise, I thought I would show you a little bit about what Hyperfuzz looks like live. In this case, we've got a relatively small number of tests, in fact, less tests than I have CPU cores, but several minutes in, we're still regularly finding stuff. And in particular, I think on a log axis, this comparison of coverage at 100 examples compared to coverage where we are now is pretty suggestive to me that the coverage feedback is worth using. You can see we go from like 3,000 branches covered up to almost 5,000 just by continuing to run with that feedback for much longer. For now, though, I will be hanging around for Q&A. And yeah, otherwise, feel free to keep going with the exercises or jump back, and I hope you find Hypothesis useful. Hey everyone. Just one thing that a question reminded me of. I thought I should mention that Hypothesis can be installed by pip from the Python package index, but also by Conda from either the defaults or the Conda Forge channel. So however you prefer to get your Python packages, Hypothesis will be there too. All right, everyone. With the sun now having risen enough to be shining in my eyes and a morning graduation ceremony for my students starting in 5 minutes, I think it's time for me to sign off. So for the 22 of you who are still live here, I want to say thanks so much for coming. I wish we could have met in person, but I hope we can meet next year. And I hope that you enjoy Hypothesis and that it's useful for you. I'll drop my email in the Slack channel. If you have any questions, feel free to get in touch. I would love to hear what you thought of the tutorial as well, like what parts were useful, what parts were not useful, and how you go with Hypothesis in the future. So thanks again, everyone. All the best, and I hope to see you in person next year.
Thanks, Zach. Thanks, everybody, for attending. So just a note, so the video for this will appear on YouTube probably before the end of the conference, but certainly after. So you can review this and go over it at whatever speed you like. And yeah, so the Slack should stay alive for the rest of the conference, so you can chat with each other and with Zach there. And thanks very much. And I will end the session now. And so thanks, everybody, and thanks, Zach.